Moving on to question 4, we've been given the equation of the circle over here with the center at P, and we've been given a whole bunch of other stuff, and now we need to determine the coordinates of P as well as the radius of the circle. So we don't need the diagram to do this, so I'm going to get rid of the diagram, and I'm going to grab this equation, and then to get the center and the radius of a circle, this is what we have to do. We need to change the format of the circle from something like this into something like this, and we do that via completing the square, and then from that we extract the center and the radius with this number on the outside. So we're going to do exactly that with this equation. So the first thing I'm going to do is put the x's next to each other, and you want them in descending powers of x, so you want the x squared first and then the x next to that. And now I look at the number in front of x and I'll halve it and then square it. So half of 6 is 3, so I'm going to add 3 squared. You always have a plus over here. Okay, now that sets up the x's. Now I'm going to focus on the y's, so I'm going to put the y squared first, and the minus 4y I'm going to put second. And now I'm going to repeat the exact same process. I'm going to half and square this number in front of y. You can ignore the signs here because it's always going to be a plus when you do this process. So half of 4 is 2, and then I'll square that. And then this 12 is going to stay over here. And then to maintain balance throughout the equation, this plus 3 squared and this plus 2 squared that I added in, I've got to put them on this side as well, like this. And by adding these numbers, I complete the square. So now we officially finished setting that up. Now we're going to jump to the next line. So bear in mind, you don't have to write this line. I'm just writing it so you understand this process better. 3 squared, 3 times 3 is 9. 2 squared, 2 times 2 is 4. The rest of the stuff stays the same. Now, I don't have time to do this. Jeez, my bro, that's going straight on the calculator. And it gives me 25 when I pop it in the calculator. A perfect square, my bro. Okay, and then what we do next is we factorize this trinomial over here, and we factorize this trinomial over here. When we say complete the square, these are the squares. They're perfect squares, and we had to add something in to make them a perfect square. So we completed the square by adding this number in for the x's, and we completed the square here by adding this number in for the y's. And now we're going to factorize both of these trinomials over here, and I've set up the shell of brackets to get us ready for that. When I factorize this, I've got to use the factors of 9 to get negative 6, and I'm going to use the factors 3 times 3 to get this negative 6. So to make that happen, I have to say minus 3 minus 3. So that means my two brackets are x minus 3, x minus 3. And I'm going to do the same thing with this trinomial. I use the factors of 4, so maybe 2 times 2. And I somehow need to add or subtract those to get minus 4. So I get that done by saying minus 2 minus 2. Which means my two brackets will be y minus 2 and y minus 2. Okay, so I have kind of over-explained this a little bit, but I do kind of want you to understand the process and what you're doing. Most people just teach shortcuts and you don't really understand what you're doing. But with this process, you see comprehensively what you're doing. So now, anything times itself is basically that thing squared. So this I can change to x minus 3 squared, like so. And I can do the same thing for the y's. Y minus 2 times y minus 2 is just y minus 2 squared. And now we have officially changed the format of the circle, so now we can extract the center as well as the radius from this form. The center, this is the x value, but the opposite sign, so it will be plus 3, and the opposite sign over here will be plus 2, so the center is at 3 and 2. And lastly, to get the radius, this number on the outside, we have to square root it, and the square root of 25 will just give me a radius of 5. And just one more thing, the center of the circle does have a name, it's P, so I'm going to change the center to a P. just like that. So let's have a look where our 4 marks are coming from. Okay, so the first mark comes from the left hand side of the process when you complete the square. The second mark comes from the right hand side when you complete the square. Third mark comes from the correct coordinates of P. And the fourth mark comes from the correct coordinates, or the correct value for R rather. Now you don't have to write this line, but I like to do it. It helps my understanding towards what I'm actually doing over here. So yeah, that's question 4.1 wrapped up. Okay, just remember to chuck your last answer onto the diagram before you do anything. 4.2 says we need to show that the coordinates of R are 0 and 6. R is quite a special point. It is the y-intercept of the circle, and the tangent for that matter. And the circle actually has 2 y-intercepts. So here's the y-axis, it cuts there and down there. So we actually going to expect to get 2 answers when we do our process now. So to get the y-intercept, you make x equals 0 and solve for y. And I'm going to need the equation of the circle to do that. So we've got 2 versions of their equation. We've got this equation that they gave us, and we've got this one that we manipulated. It's always safer to use the one that they gave you, so I'm going to use this one. So let's grab that quickly. And just while we're here, we'll grab the other equation for the circle, just so we have it handy for the future questions. So now I'm going to make x equals 0. So this x and this x, I'm going to make them 0 and then solve for y. Okay, 0 squared is just 0, 6 times 0 is just 0, so this disappears, and I'm going to take this 12 over at the same time, so I can get it in the trinomial format. Okay, now we have a crispy little trinomial on our hands over here. So we've got to use the factors of 12 to get minus 4, so I'm thinking 6 times 2 will get the job done there. And now I need to add or subtract those to get minus 4. So I need to say minus 6 plus 2. So then my 2 brackets will be y minus 6 and y plus 2. Okay, and from there I make each factor equal to 0. So y minus 6 equals 0. Take the 6 over and I get y equals 6, just as we expected. Then I put an or there, and if I take this 2 over to the other side, it becomes minus 2. So we get y equals minus 2 as our other answer. And then we just need to do like a concluding statement deciding which one is R. We can clearly see that the 6 belongs to R. So we just write therefore R is 0 and 6. Like this over here. You're not going to get any marks for that, but it's important to do that to show them. Right, so let's have a look where the 2 marks come from. The first mark comes from changing these x's to a 0. And the second mark comes from the correct factors over there. Bear in mind, you don't get marks for this because they gave it to you. Right, now this R is going straight on my sketch. And now I need to get the equation of the tangent RT, the straight line over here, in our standard form y equals mx plus c. So Euclidean geometry has officially sneaked its way into this question. We're going to have to know a certain Euclidean geometry theorem to be able to solve this. And that sneaky little theorem is tan perpendicular to rad. But I don't see a radius here, so I'm going to have to draw it to make this question possible. So I'm going to draw it from P to R, like this. So here's our radius. From PR is our radius. And now we know that this tangent will be perpendicular at 90 degrees to the radius. Tan perpendicular means 90 degrees to the radius. So I know there's a 90-degree angle there now. And that forms the whole premise of how we're actually going to get the gradient for the tangent. So I'm going to start off by getting the gradient for this radius over here. And I'm going to do that with the gradient formula. Okay, so we're just going to use our stock standard gradient formula. Now the gradient is what I'm looking for, so I'm going to leave that there. At the same time, I'm going to give it the appropriate name. So the gradient of line RP, the gradient of RP. I'm also expecting a negative gradient because it's sloping downhill, as you can see. So I've got to put a point on my line in here. You can use either one first. I like to use the top one first. So 6 will go there and 0 will go there. And now I'm going to put in a different point. So I'm going to put P in, so the Y goes on top and the X goes to the bottom. Okay, and ain't nobody got time for that, bruh. That's going straight on the calculator, my bruh. So if we pop that in, press equals, it gives me minus 4 over 3. And it is a negative, just like we expected. Alright, now that we've got that, we can get the gradient of the tangent using our perpendicular lines formula. And that formula is dictated by so, if I multiply the gradients together, I get negative 1. So I've just given you a quick example over here. And a shortcut you can learn to do is you flip this fraction and you switch the sign. So you see there, I get minus 5 over 2. So we're going to apply that logic to this particular question. So we're just going to grab this formula, and then I'm going to pop this gradient into gradient 1. And this gradient belongs to our tangent, so I can rename it m tan to represent the gradient of the tangent. And then to get this on its own, I just say negative 1 divided by this fraction. You can type it into your calculator, or you can use the shortcut we discussed earlier. So if we just pop that in and press equals, you can see how the fraction flips and it changes from a minus to a plus. So the gradient of the tangent is 3 over 4. And now we're going to work on getting the equation of this line. It is a straight line, so it adopts the form y equals mx plus c. So let's grab that formula quickly and put in our goodies. Okay, so with the linear function y equals mx plus c, m is a placeholder for your gradient. The gradient of this line is 3 over 4, so let's pop that into m's place. And the c value is the y-intercept, and quite likely we do have the y-intercept for this line. You can see it's where it cuts the y-axis, it cuts at 6. So we can replace c with 6 and our job is done. And your 3 marks over here come from the gradient of RP, the gradient of the tangent, or you can name it the gradient of RT, and the last mark comes from the final answer in the form y equals mx plus c. And now 4.4 asks me to get the size of theta correct to 1 decimal place. Theta is over here and it's not an angle of inclination. Because in coordinate geometry, there's only one way to really get an angle. It's with the angle of inclination formula. So I'm definitely going to have to use the angle of inclination formula somehow. I want to maybe use it for this line. It will get me the angle of inclination over here for that line. And then I can use this triangle over here, RTO, because theta is an exterior angle of that triangle. And then this angle over here, each little corner of the Cartesian plane is 90 degrees. So if I just say this angle plus this 90 degrees, it will give me theta. So I'm going to go ahead and get this angle using the angle of inclination formula. So if I want the angle of inclination for this line, I've got to use the gradient of this line. So I'm going to put the gradient of 3 over 4 into the gradient's place over here in the formula. And the small rule is not coming into play because my gradient is positive and not negative. Now we can start working on getting theta by itself. Okay, so I'm just going to move the tan over and it will become arctan or shift tan as I like to call it. And then just another small thing, I've labeled this theta RT so it doesn't clash with the name of this thing. So theta RT is representative of this angle over here. Okay, let's go ahead and pop that in the calculator. Okay, so if I pop that in, it's 36, comma, and I'm going to give it to one decimal place, so it'll be 36,9. And now we can go ahead and get theta. Theta is just going to be this one plus this one because of exterior angles of a triangle. You're not expected to give reasons within analytical geometry, so we don't have to write the reason down. So let's go ahead and make that happen. Okay, and let's just tune the calculator. How's it, brother? And pop them in. We get 126.9 degrees. Don't do mental maths. Always use your calculator. Your work will be more accurate that way. And lastly, let's have a look at our 3 marks. Substitution into the formula gets us our first mark. The size of theta RT, or you can say RTO, gets us our second mark, and the final answer of 126,9 gets us our third mark. 4.5 tells us a vertical line is drawn as a tangent to circle P at a point Q where A is bigger than 0, A is the x value of Q, and we've got to write down the coordinates of Q. So there's only 2 possibilities of drawing a tangent with a vertical line. The one possibility would be to draw it over here, and the other possibility would be to draw it over here. And they've kind of hinted at which one you must choose with this statement over here. They're saying A needs to be bigger than 0, which is indirectly saying your x value needs to be positive. So over here we can see that the x value of this tangent, it's on the left of the y-axis, so that one's negative. So we're not working with that tangent, so let's get rid of it. This is the tangent they want us to write down sort of the coordinates for Q for, because the x value is bigger than 0, the a value in this case. And we need to basically get this point Q. So Q is where this tangent touches the circle. So Q will be over here. And they also said write down. That means there should be no working out involved. Okay, now how we do this is we go a radius length across to get to Q. Now Q is like the same height as P, so they're going to adopt the same y value. So I know B is 2. And then remember from earlier, the radius of our circle, if we square root this, the radius is 5. So to go a radius length there, it means I have to go 5 units that way. So if I start at 3 and I move 5 units that way, I'm going to get to 8, because 3 plus 5 is 8. And that will be the a value, or the x coordinate for Q. And the 2 marks from this question purely come from the right x value and the right y value. Okay, welcome to your challenge round. For which values of k will this thing be a secant to the circle? Alright, so a secant is something that crosses through the circle twice, like this. So it's going to cross through the circle twice and it extends past the circle as well. And a secant could also look like this. It can go through the circle this way. So we need some sort of guidance on how to orientate the secant. And our clue on how to orientate it is the gradient over here, the 3/4. Because the number in front of x represents gradient, so they're telling us the gradient of your secant is 3/4, so it's going to be parallel to this line over here. So now we know which way our secant is going to be moving, and there's a lot of places we can actually put the secant. So we can like put it here, we can put it there, move it down a bit, we can move it down even more. Can move it there, we can move it even further down, we can move it there. So essentially what we want to do is we want to find out like the lowest place we can actually move it, because we are going to get a whole range of answers for k. You see here it says values, it implies plural, meaning there's more than one value of k that will make this possible. So if I go to the extreme, I turn the secant into a tangent. And the secant can be placed anywhere in between this tangent and this tangent. And the k value is in place for the y-intercept of the secant. So this little thing over here is representative of k. And this k has the freedom to move anywhere in between the two tangents. So my point of interest is this one and this one down here, because k can move anywhere in between those. So we've already got this one. He is 6. So we've got to find out what this one is, which is going to be the challenge for this question. Okay, so to get this point over here, that k will lie in between, we need the equation of this tangent. Luckily, we've already got the gradient to it. It's parallel to this tangent, so that we know the gradient of this is 3/4. And now the tricky part will be to get the c value. We don't have the y-intercept, that's what we're after. So we're going to need a point on this line to sub in to get that c value. So what I'm going to do is extend this radius into a diameter and use the midpoint formula. Okay, so we're looking for this point and we're going to get it using the midpoint formula. So let's grab the midpoint formula and utilize it quickly. Alrighty, so I will be utilizing my midpoint formula to get an endpoint. So I'm not using this one. Okay, so let's perhaps focus on the x values first. The x in the middle is 3, so I'm going to put 3 inside of xm's place. Okay, now the x's at the end, the first x at the end is 0, so I'm going to put 0 in place there. And I'll just leave this x2 because it's the x coordinate of this one, which I don't know. Now I'm going to multiply both sides by 2 to get rid of this 2. So 3 times 2 will give me 6. And 0 plus x2 is just x2, or x if you want to call it. Because like 0 plus 7 is just 7. Okay, we're starting to cook a little bit. Now we have the x value over here. Okay, we're going to rinse and repeat that procedure with the y values. The y in the middle is 2. So I'm going to put 2 in place here. And then the y values at the end, the first one is 6, so I'm going to put 6 there. This one I don't know, so I'm just going to call it maybe y, or we can leave it as y2. And then 2 times 2 will give me 4. And now I just move the 6 over, it becomes -6, and 4 minus 6 is -2. Makes sense because it's under the x-axis. And now that I've got that point, I'm going to sub this point into this equation so I can get the c value or this value, so I can get the range of values for k. Okay, so I'm just going to grab that formula, sub in this point. This blokey goes into x's place, and this -2 will go into y's place. So let's make that happen. Alrighty, I'm going to lean on my calculator a little bit to help me out over here. So let's pop that in quick. And that just gives me 9/2 for 3/4 times 6. And then I take that 9/2 over and it becomes a negative. So I'm just going to do it like this on my calculator, -2 minus 9/2, press equals, and I get my c value to be -13/2. Okay, we are nearly there. Okay, so now I know this c value is -13/2, so let's replace it here. And through that, I now know this coordinate, the y-intercept, is 0 and -13/2. And with this value and this value, I can formulate my answer. K, which is the y-intercept of the secant, can be anywhere in between 6 and -13/2. And we write that like so. Yes, this was a nasty question. Lastly, let's have a look where the 4 marks are coming from. Your first mark comes from the correct x value of the point of contact between this tangent and the circle P. The second mark comes from the correct y value for the point of contact. And then the last 2 marks come from the correct values that k should be in between. And the last question in question 4, another circle with the following equation is drawn. Will circle M touch or cut circle P, or will it neither touch nor cut circle P? Show all calculations to determine your answer. So I'm going to give you a bit of a crash course on how and what you need to do to determine this. So to find out if circles touch or cut, also called intersect, we need the distance between the centers of the circle. So we need both centers of the circles, which we are going to get. And we also need the radii, or the radius of both circles. And if the distance between the centers is the same as the radii added together, they only touch once externally. If the distance between the centers is smaller than the radii added together, the circles touch twice. If the distance between the centers, or the purple line, is longer than the radii added together, they do not touch. And if the distance between the centers is equal to the big radius minus the small radius, they're only going to touch once internally, which means the smaller circle is inside the bigger circle. So basically we're going to need 4 things to make this happen. We need the radius of each circle, and we need the center of each circle. So that's my first mission, and that's the first thing I will be getting. Okay, for this particular circle, I'm just going to read the center and the radius off of it. So the center, remember, it's the opposite sign. So the center will be at -3 and -2. And the radius of the circle is the square root of 36. And the square root of 36 is just 6. And I can name the center M, because they told me the other circle has a name of M. And now we got to go back to circle P, and we've got to get its center and its radius, which we have done previously within the first question. So if we just have a look at the first question, there's the center P, it's 3 and 2, and here's the radius. It's the square root of 25, which is just 5. So let's grab those quickly for circle P. Now next up, we need to use the distance formula between M and P. We need to know the distance between the centers of the 2 circles. So let's grab our distance formula quickly. Okay, so with our distance formula, we can put any point in first. It really does not matter. I like to put the negatives in first. It just makes the calculations a little bit easier. So this -3 will go into x2's place. And this -2 will go into y2's place. So let's make that switch quickly. Okay, now we're just going to chuck the other coordinate in. This will go into x1's place, and this will go into y1's place. Okay, and ain't nobody got time for that, bruh. That's going straight in the calculator. Okay, and then type it exactly how you see it, with the square root and everything. Press equals, and we get 2 root 13. Let's also have a look at what the decimal value is of that, about 7.2 or a 1. I'm actually going to write both of those for comfort's sake. And now I need to add the radii together to see basically how they stack up with one another. So if I add the radii together, 6 plus 5 will give me 11. So let's see what bracket that will fall under. I believe it's going to fall under this bracket here. The distance mn is smaller than the distance of r plus r. So the circles are actually going to touch twice. So we can leap to that conclusion now. So we just write a conclusory statement saying the circles will cut twice or they'll touch twice. And then lastly, let's have a look where our 4 marks come from in this question. So our first mark comes from the correct coordinates for M. Our second mark comes from the correct radius for both circles. Third mark comes from the correct distance for MP. And the last mark comes from your conclusion that the circles will cut twice.